I would say this one can lead for your self-exercise. Basically, the first equation will apply the loop law of, basically this is the first loop, and basically we're surrounding this loop, and that means this is the EMF. The voltage should be equal to the voltage drop across the three elements. And then the second loop across here on the output terminal, that means this voltage must be equal to the voltage across the capacitors. So here we have two equations. And again, this is a differential equation. These are derivative differentials, and you can take up the Laplace transform. Laplace transform for derivative, and we're going to use derivative quite a bit. So for any derivative, we know for say x dot xt. Okay, so here the x of t, the Laplace transform will be defined as the capital X of s. So for this one, if we drop in, say let the initial conditions equal to 0, then basically this is simply s multiplied with capital S. Okay, and if we have an integral of x of t dt, then the derivative, the Laplace transform simply is 1 divided by s times capital S. Okay, so for derivative, we simply multiply with s. For integral, we simply 1 divided by s. So keep this kind of symbol in mind. So many times, once later on in control, we work in the S domain, in the frequency domain. Once you see S appear, basically that really in time domain, meaning a derivative operation of the differentiations. Okay. So applying the Laplace transform to the two equations, and the two equations, one is input, one is output. The other element, those elements are the systems. So basically we can express the ratio between output and to input, and this is the ratio between output and input. This one, per definition, is called the transfer functions. Okay, and this is a typical second-order systems. Okay, compared to mechanical systems, again, here is the mechanical systems. Let me use a different color. So for mechanical systems, and you've seen before, this is M, K, and C. So for this system, if we define this is our equilibriums, and you should be able to formulate the governing equations. And for example, here I provide an external loading, and here is Ft. So by ignoring the initial conditions, so for this case, this external loading, this is our force excitations, and force excitation is the provided signal. So provided signal, basically this is in terms of the terminology in control, we call it input. Okay. And we provide a force. We want to know how the system responds. And X, in terms of the response, X can describe or categorize the system response. So in terms of control terminology, this one, X, is called output. Okay. Response means output, and given signal means input. So basically for here, for this case, we take the Laplace transform of the systems, ms squared plus cs plus k, and capital X equal to f of s. F, this is the Laplace transform of f. X is the Laplace transform of the x of t. Okay. So from here we take the transfer function, that is a ratio between the output to the input. Okay. Now for this mechanical system, that is m squared plus cs plus b plus k. Okay, so again, this is the output and to the input. So compared to the electrical systems, can you see that have a similar the pattern here, basically the same pattern but the similar coefficients. For the second order of the electrical system, basically they're composed of the LRC. Basically that is due to the existence of the inductance here that will produce the second order systems. Okay, so LC compared to here with 1 by 1 LC basically equivalent to mass, and RC is equivalent to C, and here K equal to 1. Okay, or vice versa. They have quite a few analogy between mechanical and electrical systems. Okay, and pretty much you have seen that one. So basically, all the techniques we have learned in analyzing the system response, starting from here, can be directly applied to here. Okay, and again, this is a second order system, and for this case, we have done earlier, and if you remember, and this one basically, again, here, maybe I can put a bit more time here. So for this case, this is called the transfer functions, okay, and transfer functions. And for the transfer function, do you remember the characteristic CHA-RAC characteristic equations is defined by the denominators polynomial equal to 0 of the transfer function, so which means ms squared plus cs plus k equal to 0. Okay, so that is our definition of the characteristic equations. And for this case, this one we can describe making, say, divide everything by n. Okay, so in a way we try to redefine the parameters such that this term will be equal to, so this is S. Okay, so this one we redefine the parameters such that omega n squared equal to this one and this term corresponding to C over m, etc. So this is our standard form. This is called the standard form of the second order systems. In the same way, for electrical systems, and here we have is LC S squared plus RC. So again, we can put into the standard form. We simply unify the coefficient here. So RC divided by LC and plus 1 LC equal to 0. So again, this one has an equivalent description of this one. You simply do the comparison of those parameters one to one, then you can figure out the informations. Okay. So from here, last time we did this is the pole. And so that means here we can solve for S1 and 2. And in particular, for our controls, we are more interested in this case. We call it underdamped second order system. Okay. This is the particular case we are very interested because this case can produce the oscillations response. For zeta equal to 0, for zeta equal to 1, for zeta greater than 1, there is no oscillation response. If the response has no oscillation, then its dynamics is very easy. It's very easy to deal with. So that's the reason why in control we are interested in this, because due to the oscillations, there's more work we need to do, and actually there's one chapters will be devoted to these systems. Okay, so here I kind of give you the review. So for this case, we have the roots, so that one equal to zeta omega m minus plus and omega m times 1 minus zeta squared, and this is the complex part. Okay, so this is the root. This is the poles of the transfer functions, or we can call this is the root of the characteristic equations. Okay. So for this one, we draw this root on the complex plane. So this is the real S, and this is the imaginary S. So here we label it. So this is the locations here minus zeta omega n. So this is omega n times 1 times this one. So basically one pole is here, and that is due to complex conjugate. The other one is here due to symmetry. Okay, and furthermore, the distance between the origin to the location of the pole and that magnitude equal to omega n. Okay, and this angle is equal to theta, and theta can be determined by a cosine of zeta. So that is functions of the damping ratio. Okay, and so if we have appropriate input, so for example here, so if we have a different input, say unit impulse or unit step, and that one we should be able to calculate the output. Okay, so those one will be reviewed later. So here I take this opportunity to give you another practice, and that one we have done before. So basically we review this one here. The next page, again, this is another example. Probably you can do it by yourself. And so from here we have three loops. Okay, one, this loop, the middle loop, and the loop at the terminal, the output terminal here. Okay, so that one leaving for your exercise. This page is about the operational amplifier, and electrical student engineers, sometimes they call the op-amp, and that is this one. For op-amps, basically it's using to magnify the signal from the input to the output. Usually the gain is pretty huge, to millions, 10 to the 6, and it's very common. Okay, and that is due to the design of the circuit there. So this one, this page basically is the introductions, and here is a little bit more practical. The rules, the modeling of the operational amplifier, I don't know how much you've been remembered in ES307, but here I try to rearrange in the quick way, and we won't touch too much, but just to the point we need. Okay. The rules of the op-amp is this, and this is the schematic drawing of the one operational amplifier. And we have the input terminals and output terminals. Usually input terminals are determined by 2 ports, minus and plus, okay? And given this schematics, then there's 2 rules. Basically, the first rule is barely there's no current flowing into the op-amp, okay? And barely is almost 0. So basically here we assume ideally no current coming in. The second one is because no current coming in, so that means the voltage at minus port and plus port basically they are equal. Okay, I don't know whether you teachers have given this rule in 307. No, probably they are given more complicated mathematical description, right? Or have you learned this before? No, then I can slow down a little bit. Okay. So we stick with the 2 rules, and then we see. And we look at first example here. So this example is in certain way is this. We place our voltage supply, say the power supply here, okay, and like say voltage, the batteries. And we buy the op-amp from a company, okay, and we draw on our design in terms of the symbols. And when we buy op-amp, and usually on the data sheets they indicate the positive and negative port on there, so we simply stick with that one. So for this example here, we choose these configurations such that we only use 2 resistors. One is R1 here, one is RF there. And linking in this way, okay, so this is supposed to be the given circuit configurations. Okay, that's a given one. So for us, for you, our job is to analyze what is the ratio between the output and input given these configurations. And we can do it pretty easily based upon the rules. Okay, the first rule is no current flowing. Okay. So assuming right now here through these resistors, we assume there's a current we call the I1. Okay, I1 coming through here and to this point, and he has the electron here have two options, going here and going here. But we're assuming there's no current coming in, right? So basically, all of the electrons will go this path. So basically, this current flow will go in this way. Okay, so that's the first rule. And so that means here in terms of symbol, I1 equal to IF, so that we apply the first rule. The second rule is saying that the voltage at the negative port equal to the voltage at the positive port. Okay, then we can formulate what is the voltage at here. This voltage V in is equal to sorry, let me repeat again. Because this voltage is equal to this voltage, and here is our voltage supply. So we call our supply voltage is called V in, input voltage. And because of the second rule, so that means this is V in, so therefore this also is V in there. Okay, so we apply the second rule to here to determine, okay, at this point, the voltage is V in. Okay, with this one, then we apply to the first rule. What is I1? I1 is a current coming through here. So coming through here, that is determined by the voltage difference across this divided by the R1. So that is this one, that's called I1. What is IF? IF is the IF multiplied with resistance equal to the voltage across itself. So that means V out minus V in divided by RF equal to IF here. Okay, so for the third one here, we simply apply is the basic functions Ri equal to E, resistance multiplied with current equal to voltage across that resistor. So we simply apply that one. So with those things we arrange, we found the VO output versus input equal to this one. So this is the transfer functions of this op-amp. Okay. And for this relation, this one magnitude give us is a ratio. So that means, say, if you're going to use an op-amp to amplify the voltage by 10 times, then you better to choose RF is pretty much 10 times greater than R1. For this case, RF equal to 9 times of R1, then you can do it. So that is the first features, give us the magnitude ratio of the output to input. The second one is the output and input, they remain at the same phase. The same phase, that means if the input is positive, the output will guarantee to be positive. So this is called the, so in this way they define this one as long as the output and input they are at the same phase. Then they define this configuration as called the non-inverting configurations. Okay, non-inverting, that means the phase of the input has not been inverted. So it's called non-inverting. Okay, so probably in this way you can imagine. That be okay, I move on to the next page because I know some of you kind of very diligently taking the notes. And sorry for my tones. And I know my tones has certain magic will likely put people into sleep. In particular, when I go through the slides. I'm sorry about that one. I will try to improve. I think that the best person I've been seeing really have good speech is the ex-President Obama. His speech is very, very, very effective and sometimes very inspiring just by listening to it. Whether he can make it or he can commit it to do it, don't know, but very inspiring. Okay, I think that could be the one of the characteristic. He can be the president of leaders. I think it could inspire the group. Right? I'm not, so I know my strengths, so I will try to use my strengths to hide my weakness. Okay, the second one, similar configurations, okay, and again, these are op-amp. And here we're still using two resistors, and we see what happens. And now we put our supply, the input supply to here. Okay, we still apply the two rules. And again, the first rule is we're assuming the voltage applied to here is I1. And to this point, and because there's no, by the rule one, no current coming in, so all the current will be coming in this way. So that means IF equal to I1. The second one is the voltage here at this point equal to the voltage at this point here, okay? And voltage at here, because this is connected to ground, suppose by reference ground equal to 0. So this point equal to 0. And by applying rule 2, the second rule, the voltage must equal to here. So at this point, in this configuration, the voltage at this point should be equal to 0, okay? So doing this one, and we know the current, then we apply the basic rule. So 0 minus V in, or V in minus 0, and sorry, V in, okay, this is a higher voltage, this is a low voltage, so current flowing through here. So that is I1 equal to this. On the other side, and current flowing through here, so 0 minus V out, and it provides the current coming through, so 0 minus V out equal, divided by RF equal to this one, okay? So again, the two things are basically apply the fundamental rules here. So we arranged this relation, we found the V out divided by V in, and equal to minus RF by R1. So here again, similarly, if you like to have the magnification of the 10 times, then this should be 10 times of the R1 per this relation. On the other side, because you can see here there's a negative, so if I have an input positive, then you should expect the output is negative. They change the phase, which means change the sign. Okay, due to this change, we call it inverting op-amp configurations. Inverting, that means they invert the sign. Okay, and basically that, in terms of the electrical engineer, they like to use phase. So basically, there's a 180 degrees of the phase lag or phase lead. So this is about the op-amp, and should be very easy. So the two rule, and doesn't matter how complicated, and in practice, the configuration can be a little bit more complicated, but the two rules are always applied. Okay. The next page and onwards, I simply copy that is showing the tables summarized in our textbook. And from here you can see, and basically they have a different configurations in linking, okay? And here we not only using resistors but also capacitors, but again the rules, the two rules still apply. So if you carefully practice through this one, you should be able to, not hard, to get the kind of relations. And follow up, here is a little bit more complicated, but I think it's doable. Here is in parallel combinations of the fundamental components, we can do it. So again, if you focus on the two things and rules carefully, I think it shouldn't be hard, okay? And these are the copy from the other textbook a couple years ago I used, but not use that anymore, but just provide for your reference. If you have similar design, and if you might refer to those kind of things. First one, you determine what kind of the output you like to use, so those are the transfer functions. So by picking up an appropriate transfer function that fitting into your design purpose, then from there you look for the corresponding circuit design. Again, in many ways, as a controller design, the engineers or controller designers, many times once we want to implement the controllers, we go to the electrical circuit design. And that is electronics making the controller. That is the most, not 100%, but most of the cases, usually is they match in the team with at least one mechanical engineer and one electrical engineer, and they're working together, okay? And in the past couple years, I've seen in ME senior design, they at least as a one team, they kind of working together and always have a kind of controller things coming out. Okay, they work from the circuit design, and then they implement the circuit onto the Arduino board and writing the program, so etc. Okay, so here I simply provide you the information. Now this one is the fluid mechanical fluid system, and only one page. I will do it very quickly, and basically only pretty much one rule is this. If you like to have a viscous fluid to flow through a pipe, if you want to have a flow rate, which means equivalent to the electrons, if you want to have a fluid to flow, then you must produce the pressure drop, or they call the pressure head, at the upstream, right? If there's no pressure head, then basically the fluid will be stationary, no motions. So here we call it delta P. Delta P is the pressure difference across certain distance you want to achieve. So given the same value of the delta P, the longer the distance, then the slower the flow. Okay, basically the equation is provided by this equation, and I forgot the name. Delta P is linearly proportional to the Q. Q is called the flow rate. Flow rate is in terms of the volume per time, volume per minute, or volume per hour. So that we call the flow rate. Okay, and that one in this is called the frictional coefficient. Okay, frictional coefficient determined by a few things. The one is geometry related, the length of the channel or pipe, and also the size, which means the diameter D here. And also it's governed by the viscosity. The more sticky of the fluid, more frictions. So that is mu. Mu is called the dynamic viscosity. Okay. So put this one into here, we can calculate these coefficients, and this one called the flow resistance. We take this as one example here. See how can we model this system. This system basically here is this. We have containers, we have a reservoir, and reservoir is provided by a constant flow through a piping. So basically here we provide is a constant flow rate to supply this reservoir. And also at the outlet here we discharge this fluid, and by controlling into a constant discharge flow rate. So those one, the size of the reservoir A equal to constant. So basically here we are given is Q in, size of the reservoir, and Q out. And so from here, basically here we want to model is the change in the height of the reservoir. So we see how can we do it. The first one, we look at this equation here. We know this is accumulations of the fluid into the reservoir. That means accumulations of the volume per time. That is given by A times H dot. H is the height. H dot, that means is increasing rate in the length. So this is the accumulation volume in the reservoir in time, which is governed by how much we get and minus how much we out. So that is simple. Now we can determine how to determine the output rate here. And the output rate, the discharge rate here, basically is governed by this kind of distance. Okay, assuming we know the dimension here and we can calculate this coefficient, let me just call it R. So R is the resistance coefficient for this portion. We simply name it R. And that one, per this equation, R times Q equal to delta P. So that means the pressure difference between the 2 points equal to this term here. Okay. And this is the ambient pressure, for example here, or I call the PA. And this is the pressure at the bottom of the reservoir. At the bottom of the reservoir equal to P, and P is equal to we call the hydraulic pressures rho GH divided by R. Okay, so that means this equation we can simply write it down here. And in this equation, combining the two and plug in those kind of consideration, you can see the only parameter is h dot and h here. And the other parameters are constant, they are given. So this is a one order the dynamic systems. Okay. So one order dynamic system, then compared to our second order, this system is easier in analysis. Okay. So that is the fluid system. And I skip the thermal systems because I know these semesters and in the previous semesters, most of you have been taking thermal system and thermal system lab. Okay, and I think the textbook providing the information is two very simple versions. Okay, so probably I will rely that one on you, on yourself. Okay, so that is about the modeling of the system. Then we'll go to the next topic.